In this video, we're going to talk about geometric sequences. Geometric sequences are a sequence where we multiply to get the next term. For example, if we had 2, then 6, then 18, and then 54, and so on and so on, we're multiplying by 3 every single time. That makes it a geometric sequence. The thing you're multiplying by is called the common ratio, and we denote it with an R, common ratio R. So it's very similar to arithmetic sequences where you're adding every single time or subtracting every single time. In this case, we're multiplying every single time. Just like an arithmetic sequence, geometric sequence, you can write that as a recursive function where you're just multiplying by R every single time. Or you can write an explicit formula that helps you find the 20th term or the 40th term. When we have an explicit formula, it makes that really easy. All the same terms are the same. A1 means the first term. AN means the nth term. If you want the 30th term, A30 would be the 30th term. N is the term number. If it's the 30th term, N is 30. And AN minus 1 means the previous term. AN plus 1 means the next term. And R is a common ratio. As I mentioned, recursive form is very useful to find the next few terms, while an explicit form is very useful to finding a future term, like one far in advance. Okay, so first let's talk about how to find the next couple terms. Determine if each sequence is arithmetic, geometric, or neither, then find the next two terms. This first one, if you look what's going on, it looks like we're dividing by 3 every single time. We're dividing by 3. Now that actually doesn't work as an R. R has to be multiplication. Instead of dividing by 3, we're going to say, you just flip that and say, you're multiplied by 1/3. These are the exact same thing. Dividing by 3, multiplying by 1/3. Same thing. So we had to write it in this form for a geometric sequence. The next two terms would be, well, get that 1/3 and times it by 1/3, your R, and you get 1/9. That's the next term. What is this? 1, 2, 3, 4, 5, 6. So the seventh term, A7, would be 9. If I want A8, I get that my eighth term 1/9, and then times it by my common ratio, which is 1/3, and I get 1/27. That's the eighth term. So anytime you want to find the next couple terms, just multiply by the common ratio or add by the common difference. This one, we're getting -3, 3, -3, 3. Our common ratio is -1. We're multiplied by -1 each time. Multiply by -1, multiply by -1. My next term would be 3 and then -3. That's all that's going on is you're multiplying by -1 every single time. And it's a geometric sequence. You're multiplying by -1 every single time. So this is geometric. This was this one. Now this one right here, if you look at it, we're not multiplying the same thing every single time. We're adding the same thing every single time. We're going +3 every single time. This is an arithmetic sequence. The common difference, we call it not the common ratio, is 3. I want the next couple of terms. 1, 2, 3, 4, 5. I want A6. All we're going to do is add our common difference to the last term. 14 plus 3 is 17. A7 gets 17 plus 3, you get 20. Those are common to those. The next one here, it looks like we are multiplying by 2. So this is geometric, and our D is 2. 1, 2, 3, 4, 5. We need A6. All we're going to do is get the last term and times it by 2. And you get 96. And then if you want the next term, just get that term and times it by 2. And you get 192. So that's how geometric sequence works. It's a lot like an arithmetic sequence, but instead of adding every single term, we're multiplying by every single term. So to get the next term, you just keep on multiplying. If I want A10, I can just keep on multiplying by 2 to get to A10. Now let's write an explicit formula for a geometric sequence. So the explicit formula was up earlier. So its formula is this one. AN equals A1 times R to the n minus 1. And just like before when we did the arithmetic sequence, all you need to sub into is A1 and R. We're going to leave n minus 1 alone. N is a term number. Once I want to find a term, I can plug it in for n. But before that, I just need to find A1 and R. The first one here, hey, I have my A1 and my R. So my explicit formula, let's rewrite it right here. We have it. A1 n minus 1 would be AN equals 1 times 0.5 to the n minus 1. That's it. If I want the 30th term, I would plug in 30. Now I can figure out what A30 is. The same thing with this one. At A1, my AN is equal to 25, -15 to the n minus 1. Oh, and I almost forgot. They want us to write the first 5 terms. So let's start with this one here. If I want the first term, A1, just type it in. 0.5 to the 1 minus 1. Which is just 1 times 0.5 to the 0. 18 to the power is 1, so I just get 1. 1 times 1 is 1. A2 would be 1 times 0.5 to 2 minus 1. 1 times 0.5 to the first, which is be 0.5. A3, again, we keep on plugging it in, or our R is 0.5. We can multiply by 0.5 every single time. If I get 0.5 and then times it by my common ratio, 0.5, I get 0.25, sorry. If I want A4, you get your answer and times it by the common ratio, 0.5. And now I get 0.125, and so on. I'm just doing the recursive function formula. As long as you get your answer and times it by the common ratio, you're always going to get the next term. That's an side effect. That. I can do sending over here. The first term is plug in 1 to 25, negative 15 to the 1 minus 1. That's going to be 0. That's going to cancel out. You just get 25. A2 would be 25 times negative 15, 2 minus 1, which would be 25 times negative 15 to the first, which would be negative 375. And we can keep on going that way. Or if you want to use the recursive formula, just get your answer, negative 375, and times by the common ratio, which is negative 15. And we'll get 5625. And then you keep on going to find the rest. You can either use the formula, plug in your n to find it. I'll do it that way. Let's just find A5 real quick. I'm going to skip A4 and we're just going to go straight to A5. We can just use the formula for that. 25, negative 15 to the 5 minus 1, which would be 25 times negative 15 to the 4th. All that together, I'm just using a calculator because I don't know what that is. 1265625. That's how you use an explicit formula. Just plug it in anytime, any number you want. If you want to use the recursive formula, you just keep on multiplying your answer by the common ratio, and you keep on going one by one. Okay, with that in mind, let's talk about graphing geometric sequences. The key to graphing geometric sequences, your sequence is the y value, and your x values are the term numbers. Right here, this would be term 1, term 2, term 3, term 4, term 5, and so on. The sequence is the y values, and what we're plugging in is 1, 2, 3, 4, 5, because that's how you find any term you want. In this case, our pattern is we're multiplying by 2. That's our common ratio, times by 2 every single time. Let's put multiply by 2, just make it that. Okay, we have this. Our initial value was 1, then we had 2, 4, 8, 16. I can keep on going if I want to. Over 2 multiply by 2, 6 would be 32, 7 would be 64. And if I want to graph it, let's make a table. That we're going to go to 5 or 6. 1, 2, 3, 4, 5, 6. 2, 4, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'd have to go at least 16 because that's the highest I see right now. Let's plot it. 1, 1 right there. This is all estimation. 2, 2, 3, 4, 4, 8. That's the first big jump. 5 and 16. That's another jump. And again, if I was going to do, it's an exponential function. If I was going to do 632, you would really see it. 32 is double this, would be way up there. Our graph's going to look kind of like this. And doesn't that look familiar? This is just an exponential function. Where r was 2, that'll be like our exponential function right here, where b equals 2. You'll see we will also have an asymptote right here. And in general, if r is greater than 0 for like our common ratio thing we're multiplying by in a geometric sequence, then it's an exponential sequence. It's an exponential function. That's what I was looking for. It's an exponential function. Geometric sequences and exponential functions are the same thing when r is greater than 1. If I wanted to write an explicit formula first, let's do that. That's a little easier. This formula, all I need is a1 and r. That's all you need. Our a1 was 1. Our r, we're multiplying by 2 every single time. Our explicit formula is going to be an equals 1, our a1, times 2 n minus 1. That's our explicit formula. And if I want to write this in an exponential formula, a and b are a little bit different. B is 2. Done. B is the same thing as your common ratio as long as it's greater than 0. Our a, though, is our initial amount. And remember, your initial amount is much the x-intercept, and we need x equals 0. We actually got to go back to find our x-intercept. 0. In this case, we multiply by 2 to go. If we want to go backwards, we're going to divide by 2. We're going to get 1 over 2. So this formula here would be y equals my initial, which is 1 over 2, times b, which is 2, to the x. And these graphs will get you the exact same picture. Let's do another one real quick. Now that we kind of get the concept. Here, we're going, this is our first term, or second term, or third, fourth, fifth. We'll start with 12. Then we go 6. 3, 1.5, and 0.75. I'm going to graph it just real quickly. 1, 2, 3, 4, 5, 6, 2, 4, 6, x, y. Let's plot these points. 1, 12, right there. 2, 6, 3, 3, 4, 1.5, 5.75. Like your mind, right, there's an asymptote here. You know, we haven't talked about it. You don't cross at 0. These numbers can never be negative. They can get closer and closer to 0. And our graph looks like this. Don't go past 0. It's an effect. And it's a decay graph, if you notice. And why is that? Well, look at what our r was. Each time we divided by 2. Now we can't, that's a pattern. We're dividing by 2. But I can't write that. I can't write divide by 2 as my r. You have to make it a multiplication. We just flip it, and we're saying we multiply by 1/2. That's our r. We're multiplying by 1/2 every single time. So if I wanted to write the explicit form down here, all we need is our a1 and our r. We already have our a1, and we have our r now. R is 1/2. My explicit form is going to be 12 times 1/2 and minus 1. There we go. That's our explicit formula. Now if I want to write this as an exponential formula, slightly different. Our a is our initial, which is when x equals 0, which we don't have yet. And then b is our r, or common difference b. B is our r, common ratio. which we do have 1/2. How do we find our initial value? Our x. In this case, the first term is 12. That's why a1's there. We need to find our initial value to put in exponential form. If we're multiplying by 1/2 to get to the next term, to go backwards to find our 0th term, we have to divide by 1/2, also known as multiplying by 2. Half of what gets me 12 is kind of the idea, because half of 12 gets me 6, half of 6 gets me 3, half of what gets me 12, and that would be 24. So that's my a. So my equation here is going to be y equals 24 1/2 to the x. That's our exponential graph. Okay, moving on. Let's choose a formula. Given the geometric sequence 2, 6, 18, 54, find the indicated term. We want us to find the 6th term and the 15th term. This is to show you that the 6th term, really easy to use the recursive formula to find the 6th term. If he's going to find a couple more, we want to use the recursive formula. Remember the recursive formula, all it is find the common ratio, which in this case is we're multiplying by 3 every single time. That thing is 3. And then if I want to find the 6th term, our recursive formula is this, an equals an minus 1 times 3. And let's figure out what terms we have. We have a1, a2, a3, a4. If I want a5, it's all this means is the previous terms. It's to me a4 times our common ratio of 3. a4 was 54. This is going to be 54 times 3, which is 162. Then if I want a6, I just get that 162 and I times it by 3. And I get 486. That's the 5th and 6th term. That's the 6th term that they want me to find. Now, if they want me to find the 15th term, I don't want to do this 9 more times. It'll take forever. We'll just use the explicit formula. In that case, I just need a1, which is 2. I need the r, which is 3. This is my explicit formula right here. The good thing about that formula is that all I do if I want to find the 15th term is plug in 15, sub it in. So I get a15 is just 2 times 3 to the 15 minus 1, which is me a big number. We'll put that in a calculator and we get 9, 5, 6, 5, 9, 38. It's like 9,565,938. Did you have a choice between explicit and recursive? Which one did you choose and why? Yeah, we did have a choice. The recursive is easier for the next few terms. It's easier for the next few terms. All you have to do is get your last term and times it by the common ratio over and over again to get the next few terms. But to get a longer term, like a much in the future term, explicit's better. That way I don't have to do it like 30 times. But that's the idea.